This is why I picked this one first, and we're going to do this. So one thing, be aware, it's 2 chapters. It's 1 full unit on the AP exam, but it's like 20-ish% of the AP exam total. So I did basically the length of our previous test times 1.5. So there have been 10 multiple choice questions. There's now going to be 15. There's been 2 free response. There's now going to be 3 to cover everything we have. Okay, so it's all of the stuff from chapters 5 and 6. But let's look at this question first. Let's talk through some things that we are thinking that we should do with this one. Okay. By the way, I have put the year of the test and the number that it was because I think that you can actually look these solution sets up online so that you can work through these, the ones that we don't get to, practice and prepare for that test as well. So if you look for AP Stats 2013 free response, you'll find these questions. And so it looks like this online when you're looking at it. So once you find the right section, AP Statistics past exam questions. And so you'll see like 2022, and you can click on it. On the left side is just the free response. On the middle there's the scoring guidelines, so that you can practice and prepare for that test. But we're going to go through a few of these and talk through a couple of details. So number 3, what is the first thing that you were thinking we should do to find the probability that a randomly selected full carton of grade A eggs will weigh more than 850 grams? Oh, by the way, sorry, I meant to mention this. The official party line on the AP exam free response is 13 minutes per question. The reason why I did 10 right now per question for the free response. So like this entire number 3, parts A and B, you're supposed to be able to do in about 13 minutes. So 65 minutes for 5 free response questions, and then the last free response is a little bit different. We haven't looked at one yet. But I did 10 minutes because we're focusing on just this unit. We got to know this. All right, so what did we do to tackle this question?
Alright, first thing I did was I highlighted the 3 numbers, so 840, 7.9, 850, and then I took a z-score.
So 840, 7.9, and 850, and you found a what?
Z-score.
A z-score. Why? So first off, we have mean, we have standard deviation. Z is equal to, what's that general formula though for z-score? Which mean should I use here?
840.
No, the symbol, x bar or mu? Why mu?
Population.
Population, so divided by sigma. So 850 is my value, minus my mean of 840, divided by my standard deviation of 7.9. What does that give me?
1.2658.
1.2658.
So
Z-scores.
Does it matter if I use x bar or mu? Or would I even have to write at that point?
So what you can do is you can just write this, but there's going to be times when you want to be intentional about this and think through those things. So I'm always going to practice doing this personally.
They would have counted wrong if you use the wrong mean.
So
X bar was supposed
I don't, they would probably consider that extraneous in here and not count it against you, but there's a chance that sometimes we're like, you use the wrong notation and it goes automatically from an E to a P or something like that. So be intentional about this. So like, why is this mu and not x bar? So notice it's a simple thing. The question is it a sample that we're looking at for these this mean and standard deviation?
no, you have a distribution.
That's a distribution, right? So that's a population, right? It's not a sample, so don't use x bar and s. Use mu and sigma. Okay, so what are we going to do from there, though? Because there's actually one thing I would have done even before this.
Draw the
Draw a curve. Which curve? Normal distribution, right? Always, guys, y'all are killing me. Even on the demonstrating understanding, some of us forgot to draw that normal curve. But standard normal curve, you could use that mean and standard deviation, but honestly, I don't feel like going by 7.9 personally, which is why we converted to a z-score, because when we're using z-scores, what's our mean? 0, standard deviation of 1. And so 1.2 somewhere in here. Right, so there's my z. And so which direction should I shade? To the right.
Right.
That's more than. So
Yeah.
once we go to the, and so notice this notation here shows that I understand what the mean is. I should know what the standard deviation is, right? I know what my, is this upper or lower bound?
lower bound.
Lower bound. and I know it's shaded to the right. So that's all you would have to do besides then saying the probability that z is greater than 1.2658 was equal to what?
0.1028.
Okay, so let's check the free response questions. That's personally what I would have done. I would have drawn that normal distribution, I would have shaded to the right, I would have used that z-score, and the AP exam said this. So the exact answer that they did, if I zoom in here, you can see it more clearly. Nope, too much zoom. There we go. Alright, so they said let W denote the weight of a randomly selected full carton of eggs. W is a normal distribution. Would that mean that standard deviation? Z-score, exactly what we got. That probability. Notice they did 1 minus, but did they have to do that for A?
They did what?
They did, so they actually did 1 minus 0.898. Where's that coming from?
They got they used that as the upper bound.
They used the left side. So so this is in 2013. In 2013, calculators were not as normalized on the AP exam, like they were used, but you'd have to use a lot of times a table. I showed you all that normal distribution table, and so remember that table always does the areas to the left, but we don't have to worry about that. We have a calculator.
I thought we
So
weren't required to do z-scores.
you're not required to do z-scores, but I highly recommend it. You definitely need to draw it. You need some way to indicate mean and standard deviation. Here's the thing. I need y'all to hear me clearly on this. There are some things that I know that are coming up, which is why I recommend you use z-scores. Trust me and convert it to a z-score. And it's going to be easier to do the standard normal curve because now my mean is just 0, standard deviation of 1, instead of having a mean of 840 and a standard deviation of 7.9. Like that would be 847.9 and then 855.8, right? Like instead of dealing with those ugly decimals, just use the z-score distribution. That standard normal curve is built off of the z-scores. Alright, so let's see what the AP exam said though for grading. So part A, essentially correct if you use a normal distribution, clearly identifying the correct parameter values. Notice what it says, a z-score is sufficient. Because when I put in that z-score, I know the parameter mu and sigma. Right? Notice it does say parameter. How's that different than a statistic?
The whole population.
When we say parameter, we're talking about the population values. So we would want mu and sigma here. So by doing the z-score this way, I am clearly identifying that I know it's a parameter, a mu and a sigma. Alright? Did we use the correct boundary value? Yes? Did we report the correct normal probability with considering 1 and 2? Yeah. So that's an E. If you did it this way.
So if you didn't write the equation out, would you get partial?
That's what I'm looking for right now. They have these notes down here. One thing I would say is ignore number 2. That's what we're about to go into with sampling distributions.
So like if we did the normal distribution and then the lower bound, right? Would that be partially? Right?
Say that one more time.
Okay, so if we did the normal distribution
Right.
and then we shaded it in one.
And you got lower bound.
Yeah, and we didn't get the right answer, is that partially or incorrect?
It would be partial.
Okay.
So what happened that you didn't get it? Just put it in the calculator wrong?
I think that, I don't.
So value, mean, standard deviation. You did PDF. We need a CDF.
Yeah.
Alright, Bryson, to answer your question, right here, an error in statistical notation lowers the score 1 level. So you're asking about like mu and sigma versus x bar and s. So if you used x bar and s, they're not parameters, they're statistics. So that would have lowered your score by 1 level.
So like, when I answered it, I did the equation in my calculator, and I got the z-score. I did everything in my calculator basically, and then I drew the graph, shaded it.
But
put my
show the work.
Mhm.
Like I'm not doing that by hand, but I'm writing out what I put in the calculator,
Yes, sir.
and then that's what gives you the credit, right? So you got to recognize like the readers need to understand that you know this, right? And so you can say, hey, I have the final answer and it's right, but the fact of the matter is, and you see this on the AP Cal stuff as well, the steps in between matter, and you get credit for the steps in between. So even if you get the wrong final answer, right, if you show these steps in between, that's going to be credit. And so you want to show them evidence of understanding on the way there. So whatever you, guys, let me say this clearly. If you put something in the calculator, you need to put something down on that sheet of paper that makes it clear how you got that in the calculator. Does that make sense?
Yes, sir.
So if you are putting something in the calculator, make sure that you put it also on the paper in some way. Alright, so B, the weights of the empty cardboard containers have a mean of 20 grams, standard deviation of 1.7. It is reasonable to assume independence between the weights of the empty cardboard containers and the weights of the eggs. It is also reasonable to assume independence among the weights of the 12 eggs that are randomly selected. Let the random variable x be the weight of a single randomly selected grade A egg. What is the mean of x? How do we approach this?
I set up an equation, I said 12 times mu sub eggs plus mu of cartons equals mu of total weight.
Is that true? If we do 12 times the average of the eggs plus the average of the carton, should that be the average of the total weight that we're looking at?
Yeah.
What concept is that going towards? We sure did. This is which one?
Transformations.
See, that's where I need you to be careful. It's not transformations.
Combining. with-
This is combining. I'm looking at multiple variables here. I know the 12 times, and this is why I'm very clear about this. I know that the 12 times makes us think transformations, but it's not really 12 times. Like, I can simplify it that way, but what it really is the average of the eggs plus the average of the egg plus the average of the egg. How many times? 12 times. And because I'm adding the average of those eggs 12 times, I do 12 times the average of the eggs. And so notice, it's not taking one variable and multiplying it by a constant or adding or subtracting. It's combination of random variables. That's why we need to be clear on this. This is a combination of random variables. So we're adding and subtracting random variables, not constant values. And that matters more for the standard deviation than anything else. Does this make sense? What questions, what things were we thinking other than that led us astray, or do we have questions of
I
that?
had an idea, I just didn't really know where to start.
Does that make sense? So like and I mentioned this before, the combination of random variables was one of the things that took me the longest to figure out, but once I figured it out, I was like, holy crap, this makes sense. And we covered that for almost 2 days for a reason, maybe a day and a half. And so we just need to recognize that if we're looking at these 12 eggs and we're talking about independence, I'm adding the average of each egg 12 times and then adding the carton. And so how am I going to figure this out from here?
So you know that the carton weight is 20 on average.
Okay.
Total is 840. So
And where do we have that 840 from?
that's the cartons.
That was the earlier, right?
Yeah.
They told us?
So I just removed the 820 to make things easier. Then I divide everything by 12. So
What?
So I'm just casually dying.
It's okay, you got this. You'll survive, I promise.
Alright.
So just solve that equation. So what's the average of each egg?
and that'll come out to like 68.3
68.3
grams.
grams, there we go. Alright. So we want to recognize a combination of random variables. If we were gone on Tuesday, this is something that we started on Tuesday-ish. We wrapped up yesterday, so that is something that we want to pay attention to.
So all I did was I got like a mean from here and mean from here, I subtracted it, that's simple.
Yeah, I would.
I didn't
We'll
all
check.
add
We'll
that.
check on the AP rubric, but I don't know that you necessarily need to write an equation like that. But I would say that you probably need some indication under showing that we understand this is a combination of random variables. They don't just want you to do a procedure; they want to see that you understand the concept as well. That's what gets you essentially correct, the concept and the procedure. okay? And this is important for the next part. So standard deviation then, how am I gonna tackle the standard deviation?
You're just gonna add variances.
Okay, so I have to, and this is where it was important, because I couldn't just do 12 times the standard deviation of the eggs. It would be the variance total is equal to the variance of an egg plus the variance of an egg plus dot dot dot. How many times are we going to have the variance of that egg there? 12 times. And at the end of all that, the variance of the carton. And so I would simplify this. I'm going to write it over here at this point. But what was the total standard deviation? Was it 1.7? No, that's this.
Total was 7.9.
7.9, that's what it was. So the standard deviation was 7.9 squared plus, or equals, we don't know the variance of the egg yet, but we have 12 of them, plus the variance of the carton was the standard deviation was 1.7 squared. And then I just solved this equation, right? And I would heavily use that calculator. And I would literally just put 7.9 squared minus 1.7 squared in that calculator. What is 7.9 squared minus 1.7 squared?
Why'd you do 9.52?
Huh?
Why'd you do mine?
Subtracted 1.7 squared from both sides. Because remember, that's the total, right? Here's my eggs and there's my carton. What is it?
59.52.
59.52 is equal to 12 times the variance. And I will say this, you may not have thought to use this notation, but I really like Tyler using this notation because this clearly shows an understanding of the variables at play, right? Not just randomly doing stuff, but using the variables of the problem. Now what would I do?
Divide by 12.
Divide by 12.
And then that would give you 4.96.
Anything else, or are we done?
Take the root.
Take the
and
root.
that's the final answer. So it should come out to 2.227.
Wait, so why'd you divide by 12?
Because I was solving for the standard deviation, right here. And this is why setting up an equation is useful. Because we had 12 eggs, right? So 12 times the variance, because remember, we were adding the variance of the egg how many times?
12.
So I had 12 times the variance of the eggs. And I'm trying to solve for the standard deviation.
Why can't you square root and then divide by 12?
You can, but it can get messy. So let me show you what that would look like.
Well, that's exactly what
Well, here's the issue with that. Did he give you the same answer?
No.
So here's the thing, whatever you do to one side of the equation, you have to do to the other, correct? So like if I take the square root, I have to take the square root of the right-hand side, and take the square root of the left-hand side. So what's the square root of 59.52?
7.714.
7.714 equals, and then the square, I would have to take the square root of 12 still, times, and the square root would cancel out that square. Notice now, I would have to take the square, divide by the square root of 12. Why don't you do 7.714 divided by the square root of 12?
It's the same number, pretty much.
Did you get the same number?
Yeah.
So it's about the order. So like it's doable, it is, but whatever you do to one side of the equation, you have to do to the other. So taking that square root, you would also have to take the square root of 12. So what I always teach in Algebra 1 and Algebra 2 is this. Read this equation with me, right? We're not actually going to solve this all the way. What is happening to x first? Minus 7. Then what's happening to x minus 7?
It's squared.
Squared. What's happening to x minus 7 squared? Being multiplied by 3. Then after multiplying by 3, we are adding 4. That last operation, Josh, that's the first one that I want to undo. The last operation is the first one you want to undo. Now, what would be the last operation that's being done? What's the last operation?
3 times.
3 times, so what am I going to do? Okay? That's not the only way to solve this. There's other ways, but that's the most efficient path for So when I see this, was it 59.52 times equals 12 times the variance of eggs, I'm solving for standard deviation. First thing happening to standard deviation, it is being squared, then it's being multiplied by 12. That last operation of multiplying by 12 is the first one that I'm going to undo. It's not the only option, but it's the easiest option. If you still follow the math, it works out either way. Yeah.
Can I get Alexis's stuff?
Yes. Remind me of that later when we get to that point.
I'm her neighbor, so I'm gonna copy it over to
Can
her.
I leave 4.96 like root?
As a square root?
Yeah.
Probably. Let's check what the AP exam says. By the way, notice it did not ask you to interpret these things, but pay attention because a lot of times the AP exam will ask you to interpret what that mean and standard deviation are. Alright, so part B-I essentially correct if the response correctly uses properties of expected values to set up the correct equation to be solved and correctly solves the equation. Or if the response follows a correct numerical procedure to find the correct expected value. So notice they also did, let me erase, actually I'm not going to erase yet because I want to look at it. They did it this way, and I do actually really like this, right? The total weight is the carton plus the 12 eggs. And that's why we know the expected weight, or mu of sub w, is mu sub p plus mu sub x1 plus mu sub x2, right? So recognizing that we are repeatedly adding random variables is a combination of random variables. And so that's how they did it. And I like that. Same thing here with 2. What did they do? They used the variance, and we just used sigma squared. Does that make sense? What questions do you have? Sounds like we're feeling okay about that?
So we look over that type of question originally.
Yeah, we can look at it more. Alright. Let's go over the demonstrate your understanding at this point. And then we will do some more for response. At least one more for response. Okay. If I were you, I would probably grab a calculator over the weekend to help you prepare for Monday. How about this, Josh? To make it a little bit fairer that we delay until Monday, I want y'all to do at least one, maybe 2 of those free response questions. I'll answer questions about the free response questions to start class tomorrow to help review a little bit before we get into the next unit. Does that sound fair?
Yeah.
I just give up at this point.
Why? You're doing well and you're understanding the concepts. Why would you give up?
Apparently not.
Who's the AP classroom?
Let's move on.
Classroom people?
Josh, get out of your own head. You are understanding these concepts well. All right, number 10. You don't have to draw anything out here with this one. What do we want to recognize about number 10, though?
It's a.
That it's not a fair coin.
Okay, so it's not a fair coin, but it's a what? How do we know this is binomial here?
You get heads or tails.
Heads or tails, so check your bins, right? It's binary. Are they independent trials? Does one trial affect the next?
No.
No. So, right, binary, independent trials. Is there a fixed number of trials?
Yes.
Yeah, well, how many?
25.
25, and is it the same probability every time?
Yes.
So, which binomial would we do, though, in the calculator?
C.
The cumulative.
Cumulative, right? When it's more than just 1, 15 or fewer, that's cumulative, right? What would be the lower bound here?
0.
The lower bound is 0 because it's just fewer than, and upper bound is 15. Do we need to go through how to use that calculator to do this binomial CDF? Yes? Okay. Calculator page, right? Menu. And we're dealing with probability. Different distributions. And this is why we want to identify the distribution, so binomial knows we want CDF. You're right, CDF. 25 trials, 0.65, 0, 15.
I am dying.
You see it now?
Oh,
Makes sense?
Now you're
And yes, guys, we're also going to talk about the formula just a hair because some of us got a little lost on the formula multiple choice question later. All right. So, really quickly, let's talk about number 11. Okay? How did y'all tackle number 11?
I use the spreadsheet.
I would definitely use that spreadsheet.
Oh, which one?
Number 11.
Oh, I just found the median.
Okay? You found the median.
Yeah, because the median is like their expected value. 'Cause it's the
Ooh, be careful. Did you find the median or the mean?
I found it another way, and then I also found the median. As
Because,
value.
so like, here's the thing, right? You could do this by hand,
Yeah.
but that's the mean, not the median, right? That's the expected value of x. So when we say expected value, we mean mean.
Yeah, I think it was the mean.
Okay, so notice, and this would be a quick way to do this actually by hand, right? Because what's 0 times 0.3? So value times probability.
Nothing.
0.
So 0 plus 1 times 0.2
0.2,
plus
0.6,
0.6
0.3, 32.
Okay, so we're just multiplying the values times the probabilities. And so we get 0.8, 1.1, 1.42. So the expected value of x is 1.52. Okay? Notice that is not an answer choice. Because what does that 1.52 represent?
Number of shirts.
The average
Number
of
Of shirts expected to sell, correct? And so I can use the list and spreadsheets on the calculator, but also, what concept is at play here?
transformation.
This is a transformation. Every single value is being multiplied by what? A 25, a constant, right? This is a simple transformation of variables. And so remember earlier, like we were looking at adding and subtracting random variables. Here we're just multiplying 1.52 by what? By 25. Type 1.52 times 25 in that calculator. I believe you get 38.
Yep.
Okay? So we want to notice, because and the easy way to notice it is, right, if we sell 0 sweatshirts, how much money is that? If I sell 1 sweatshirt, how much money is each sweatshirt? 2. Notice that is a simple transformation of those variables, multiplying everything by 25. And so the mean would be multiplied by 25.
So what's the difference between transformation and
Combination of random variables.
Yeah.
So remember, that's what I was saying earlier, transformations are where you are adding or multiplying by a constant. Like if it's a constant value at 25, it's a transformation. If I am adding different random variables together, like 12 eggs
Oh, I got it.
and a carton, those are each a different random variable, and I'm literally combining them. Yeah. All right. Again, though, you can use the calculator. If you're not sure how to use that calculator with list and spreadsheets, stay during advisory, and I'll show you. Yes,
Can
Bryson.
we go in depth about number 12?
No, I refuse. So, number 12. Let's look at it. We've got a carnival game. Person can win a prize by guessing which of 5 identical boxes contains the prize. After each guess, if the prize has been won, a new prize is randomly placed in one of the 5 boxes. If the prize has not been won, the prize is again randomly placed in one of the 5 boxes. Hey, what are we dealing with here?
Combination? Or like,
Maybe. Say it again. Why is this binomial? You either get it or you don't, so it's binary. Does one trial affect the next? They're independent. That's why they're saying they replace the prize every time so that you can't guess a different box and just hopefully get it. Independent trials. Fixed number of trials. Yeah, I think it's 4 of them, right?
Makes 4 guesses.
Yeah, it makes 4 guesses and we want to get exactly 2 times. And is it the same probability every time?
You get 12, right?
It's 1 out of 5, isn't it? So, look at your formula sheet. Under binomial, what is the formula for a binomial? N choose x times p to the x times 1 minus p to the n minus x. Look at your probability section,
Right there.
and we're looking at binomial distributions, right? And so you do, so let's break this down. So let's ignore this combination for now. What does P stand for again, though? Probability of success. What's the probability of success? 0.2, right? 1 out of 5. And how many successes do I want? 2. So it's going to be 0.2 times 0.2, or 0.2. And what's 1 minus P? 0.8y. That's the probability of failure, right? And so I'm going to fail how many times? Twice. Notice if I take my number of trials 4 minus my number of successes, that gives me my number of failures. What's your question? Sorry, guys.
You take your number of trials.
And you subtract the number of successes. Because if I win twice, that means I have to fail how many times?
Twice.
For there to be 4, right? So if I take my 4 total number of trials and I take away my number of successes, well, think about it this way, success plus failure equals total, right? So the number of failures is the total minus the number of successes. Total minus the number of successes.
Yes, sir.
And so it looks like this, but notice, that only is the case if I win, lose. Is that the only way, though, to have 2 successes?
No.
No, I could win, I could lose, I could win, I could lose. I could win, lose, win, right? There's multiple different ways to do this. That's where we get a combination, right?
Yeah.
And so that's what this symbol right here means, that combination of n choose x. So, does anyone remember? So first off, just looking at the answer choices, there's only one option left.
Yes.
Which one? But D is only this part. I still have this. So it has to be E. It would have to be E. And this is how the AP exam is set up. Now, I will point this out. Could you have just done binomial PDF, calculated that probability, and then compared it to each of these? That's another strategy to approach it, right? But n choose x.
So, what is E saying? Like, can you talk through the answer?
I'm doing this right here. So notice, we already talked about this, right? 2 successes, 2 failures. You good with that?
Yes, sir.
Okay. So when we do n choose x, notice it's not a fraction bar. This is a thing called a combination. N choose x, or n combination x, that starts as n factorial divided by n minus x factorial, and then you divide by x factorial. And I'm going to go over this somewhat quickly, but this is in the video from last Thursday. Is that when we had the last game? The first game from last Thursday, because we broke it down here. I believe that's when we did it. But when we look at this, what we're saying is a factorial is quite simply, well, first off, what's the number of trials?
4.
So that's 4 factorial. Divided by n minus x would be 2. And then x would just be, that is what's right here. 4 factorial divided by 2 factorial times 2 factorial.
Yes, sir.
So that's what a combination is. That's how we write it out. Now, as a quick reminder, so while you're writing those notes, I'm going to finish setting this up. Okay. So Bryson, right here, this is every combination of 2 successes and 2 failures when I have 4 trials.
Yes, sir.
How many is that?
5. Or 6.
6, right? 4 factorial is just 4 times 3 times 2 times 1. Divided by 2 factorial is 2 times 1 times 2 factorial is 2 times 1. Notice that cancels. What's 4 divided by 2? And what's 2 times 3?
6.
That combination, this combination right here is identifying how many different ways I could get 2 successes and 2 failures. That's what a combination does.
Yes, sir.
Does that at least make sense for where it's coming from? But again, unless it's a multiple choice question where they expect you to know the formula, you just put it in the calculator. Which you still could have just put binomial PDF with that probability and that number of successes in the calculator and just figured out which of these gives you the same value.
Yes, sir.
Okay? Yes, sir. No, never allowed to use the restroom ever again for the rest of your life. There you go. Alright, 13, 14, 15, 16. What's the key to tell us that this is geometric? Number 13?
Until you get one.
First success, right?
Yeah.
Why is it PDF instead of CDF?
It's a single.
It's only a single trial, right? PDF is that probability distribution function. CDF is the cumulative density function. All right, 14. What do we have?
D.
Which one?
D.
Why is it cumulative and binomial?
Okay, let's see, it says at most 4, so that right there tells me it's cumulative. And
Right, at most 4. It's more than one option. So cumulative, what else?
I know it has to be binomial, mainly because like it can't be normal and it can't be geometric.
So why can't it be geometric? Because this is the real key, and this is what we gotta pay attention to.
It's not a situation where you're looking for like one thing or a group of things after a certain amount of failures.
Okay, so the first success after number of failures. So remember, geometric is the first success after however many failures, right? But also, I'm going to point this out. Geometric and binomial, it needs to be binary, right? Success or failure.
Yeah.
The trials need to be independent, right?
Yes, sir.
Each one needs to have the same probability, right? So what's the difference between binomial and geometric? Binomial has a fixed number of trials, right? The binomial is the fixed number of trials. 15 trials, that's all I'm looking at. That's how I know binomial right away. And geometric, again, is the first success. Okay, binomial, fixed number of trials, and how many successes we have in that trial. Geometric is first success. All right, 15. A. Fixed number of trials, right?
Yeah.
It's binomial.
And it's a PDF
Binary.
because it's just one single try. There's one single value we're looking at. And 16 is E, cumulative and geometric, right? So it's cumulative, fewer than 4, and again, it's the first false positive, right? The one thing I will point out and be careful about, with a binomial, what's the lowest lower bound, or what could the lowest lower bound be? 0. But with a geometric, the lowest is a 1, because we have to have at least one trial to have a success. So don't forget that. That's one small thing there.
Can geometric be, well, it's all chance and probability, but like, I don't want to say bias, but could it misrepresent something?
Well, it's just probability, right? So it can't misrepresent something. It is the probability that it takes that many trials. Does that answer your question?
Yes, sir.
You sure?
It can't misrepresent because nothing's in stone, like anything's possible.
Correct.
It
And
is
that's
all
that sampling
chance.
variability idea, right?
Yes, sir.
The other thing is, be careful, guys, when you use the word bias. Bias is only this, right? In statistics, bias is only this idea of a sampling method such that your samples consistently misrepresent the population.
Yes, sir.
So be careful with that word bias. That's the only thing that we mean in bias, or with bias. Well, we're going to talk about biased estimator soon, but it's a similar idea. All right, 17, got a lot of us. Looking back at it now, based on what we've already talked about today.
I forgot to multiply by 10.
Yeah, I forgot that.
What is it?
I forgot to multiply by 10.
Okay.
I didn't know this.
Yeah.
So why do you want to?
What concept are we looking at here, guys?
Very much.
Combination of variables.
We're looking at a combination of random variables, right? We have 10 different bars, and each have their own values, right? Their own mean, their own standard deviations, and we're looking at a box. So the weights of the bars are normally distributed with that mean and the standard deviation of 4 ounces. And so what we're looking at is the weights of the boxes filled with 10 bars expect to be normally distributed with this mean and a standard deviation of what? Well, first off, can we add standard deviations? No, we have to add their variances. So the variance of the box plus the variance of the bar, and how many bars do we have? 10. We need to recognize that we're adding these different random variables. And so the box was 8 ounces with the variance, so 64 plus, what's the variance of the bar?
16.
But that 16 is being multiplied by
10.
10. And so the variance of the total, right, is equal to that. And so what do I need to do now? So 160, 224, what do I need to do?
Take the root. And you're done.
I just felt it. What kind of box is that big?
It's holding
So
weightlifting. ball.
don't forget,
Oh, it wouldn't.
you cannot add and subtract standard deviations. You add and subtract their variances.
I'm so
It
lost.
would rip through the corner.
What do you want on?
So why wouldn't you just add
It
them?
was like,
Wait, why are you, okay. So for combination, you multiply it.
No. Right here. We added the variance of the bar how many times? 10 times. So the variance of this bar is 16. The variance of this bar is 16. The variance of this bar is 16. But I have 10 of those. It's not a transformation. It's because all those variances are the same that I just multiplied by 10.
Okay, so what if this was transformation? What would that be?
Well, remember though, so we gotta keep in mind, combination of random variables, we're adding random variables, we're adding variables. A transformation is literally just taking the value and multiplying or adding by a constant. We don't have a constant here, so it's not a transformation. Number 18, a lot of us got distracted by E, but it was actually C. What do we mean by standard deviation? On average, the number of people living in a household varies from the mean by about 1.8 people. E is actually tied into what we're about to study. E is what we're about to study. Yes, ma'am. So be careful about that. E is what we're about to study. But again, when we say standard deviation, that's the typical amount the data deviates from the mean. That's all that is. Yeah.
so why is it not E?
Because it's not talking about a random sample, it's talking about the typical amount that the data, so the number of people, it's the typical amount the number of people living in a household varies or differs from the mean. E is saying for a random sample of households, the average number of people per household will be, well, that's the other thing. This is saying that it will be 1.8 people away from the mean, but it's not it will be 1.8 on average, or it'll be 1.8 typically. That's what you need to be careful about. That's a big no-no on E, is that it's a typical amount that the data deviates. But it's not what it deviates by every time. Nope, never lied, Josh, remember again. What's up, Logan?
Nope, this ain't eyeball 16.
Huh?
Nope, the variance gets 16.
Well, what's the standard deviation? And variance
Oh,
is
squared.
standard deviation
Gotcha.
squared. Just like 8 became 64, right? Variance is your standard deviation squared.
Yeah.
Alright. 21, I think we were okay on 21. Notice, Deacon, though, 21, you see how we're relating two different variables, but we're just multiplying by a constant?
Yeah.
That's a transformation, right? Huh?
Okay. Yeah.
So 21 is a transformation. Now, don't forget, why is it, where is it? Why is it E instead of B? So the answer is E, right? It is skewed right. When you transform, does it affect the shape whatsoever? No. Transformations do not affect the shape. And I will say this, hey, really quickly. What if it was this transformation? What would happen to my mean and what would happen to my standard deviation if it became this transformation?
You add the mean, the 200 goes into the mean, it doesn't go into the standard deviation.
Right, just if we add 200 to everything, it's still the same amount of spread, right? So the standard deviation would stay the same, but the spread, the mean would increase by 200. Okay? The mean would increase by 200. How are you feeling about that? 22, A simple way, so first off, remember, continuous means it's on an interval. By the way, Ashton, I think I wrote this on your sheet. Can you, can I see, not that one. Sorry, this one.
Yeah.
Is that right on here? Yeah. So on number 1, we discussed yesterday a discrete random variable. I gotta tell you, the textbook has one of the, discrete random variable, the textbook has one of the best definitions to explain it. So use your textbook to your advantage. Read through that joker. I promise you, you will not regret it. When it said in the textbook, the way they define a discrete random variable is a fixed set of values with gaps. That's a discrete random variable. It doesn't have to be integers, but it is a fixed, and it doesn't have to be infinite or finite, right? It's a fixed set of values with gaps in between them. So when we talk about those discrete random variables, when I talk about the number of defective lights in your school's main hallway, is that a fixed number of values, or could that be on any interval? Fixed, right? What are possible options for the number of defective lights? 1 or 2 or 3. You see how there's gaps in between them? There is no 1.5, there is no 1.7, there's no 1.22, 3, 4, 5. It's gaps. That's how we recognize it. Another thing to remember is, in general, it's discrete if you can what? Count. Typically, it is discrete if it is something that you are counting. It is continuous if it is something you are measuring. Okay? The one reason, though, I say typically is this. It's not always true. If I was to talk about shoe size, is shoe size discrete or continuous?
Discrete.
But I can't count it.
Gaps.
There's gaps, right? It's a fixed set of interval, or fixed set of values. Talk about shoe size, 8, 8.5, 9, 9.5, 10, 10.5, 11, 11.5. You can't get outside of those fixed set of values. Yeah, you can't get that. You can get inches or feet for your shoes, or the length of your feet, but yeah, you cannot. It's important to recognize that. So if it's counted, continuous, or discrete, if it's measured, continuous, but again, that definition is really useful. All right. Once again, 23, 24, or 23 here. What is the first thing you should do? Sketch it out. I'm only going to look at part C quickly. So part C, when I sketch it out, here's a huge thing. You got to pay attention to this. I'm going to use the standard normal curve. By the way, you can do stuff like this if you want, so that it's not solid lines. It's probably a good idea. Just estimating, where do you know 10% could be roughly?
Between -2 and -1.
It's probably somewhere in between here, right?
Yeah.
Because I know, based on the empirical rule, half the data is to the right of the mean. 34% is in between 0 and -1, right? So here's 16%, and below -2 is about 2.5%. So it's got to be somewhere in here. And I don't have the z, which usually I have the z, right, and I want the area. I don't have the z, I have the area. So when I go to my calculator, I'm going to use what? Inverse normal. So remember, if you have the area and you want to go backwards to the z, you're using inverse normal. If you have the z and you want the area, that's normal CDF. What's up?
Could they count off if you just like put it like below -2? Like
Probably not. I'm just thinking strategically. Now I will say this though, once you calculate it and you get that z is, what was he, -1.28?
yes.
Once you get that, you should correct it and put it between -1 and -2, right?
I didn't put any like of the like deviations. I just put like
I get that. I would, just to make it make sense. That's just me. All right.
What, for 1980?
Okay.
You did not see it.
And we do not have, this is a whole lot of problems. All right, let's do this. Here's my recommendation. Hey, before you take your test on Monday, I would do 2011 Form B number 3. That is one that I think is very doable based on what we've been discussing. That's why I'm leaving it off. I would do 2010 Form B number 5. That's a very doable one as well.
Because 2011, big.
Yeah,
And then you said 10 Form B.
yeah, they should be in order. And I would do 2018 number 3. Okay. No, because I didn't go on to the second page, or maybe barely. I mean, I would legitimately, hear me on this, guys. I would do all of them at some point before you take your test. However, I will say this. Those are the 3 I would focus on. I would try to do as much of those as possible. I think, and I would check my answers against the free response solutions. I would try to do as much of those 3 today. And come in to ask questions tomorrow. The one thing I want to talk about really quickly though, there's one thing I want to talk about. Right here, okay. Because this 2010 Form B number 4 is a little tricky. So I want y'all to look at this one quickly. I chose it intentionally based on what we've discussed. And then we got to get to the next unit with at least a little bit of time. All right. An automobile company wants to learn about customer satisfaction among the owners of specific car models. Large sales volumes have been recorded for 3 of the models, but the other 2 models were recently introduced, so their sales volumes are smaller. The number of new cars sold in the last 6 months for each of the models is shown in this table. The company can obtain a list of all individuals who purchased new cars in the last 6 months for each of the 5 models in the table. The company wants to sample 2,000 of these owners. So for simple random samples of 2,000 new car owners, what would be the expected number of owners of Model E and the standard deviation of the number of owners of Model E? What do you think we should be thinking about for this problem?
So first thing I do is I take a mean, but
How are we going to get the mean there?
I think for I think expected value is like fairly easy. I think it should be like 15, and that's simply because like out of the 297,000, that 2,300 or so comes out to be 0.007 of that. So I just multiply that by 2,000.
2,000.
and
So-
it'd be like 15.
I want everyone to pay attention to this. So what is Ashton looking at? Because this is what you want to think about. If you can identify what type of probability this is, your formula sheet could be very helpful. Anybody know what type of probability we're looking at?
It's discrete.
So first off, it's discrete, isn't it? Is it one of those special types of discrete though?
No.
Sure about that?
What types of discrete are there?
It's on the sheet. What does it say under discrete?
Oh,
Binomial and geometric. This is binomial. Why is it binomial?
You're either E or not E.
It's either E or it is not E. It's binary, isn't it? So I'm thinking binomial. And so notice what Ashton said. If we look at that formula sheet and we look at the expected value, doesn't it say N times P?
Yeah.
And isn't that what Ashton did? The sample size of 2,000 times the probability of getting someone from E is 2,323 out of 297,354. And the reason why I say it's a little tricky is this. This isn't actually a traditional discrete random variable. With discrete random variables, we have the random variable and then the probability, right? But this still is a binomial in that regard, right? Sample size times the probability of success.
That's all dictated off the question itself. Like the single question told you that it's binomial, not like everything else.
Yeah,
You know what I'm saying?
yeah. I mean, the fact that it tells me that it wants an expected value, expected number, right, makes me think about mean, but also that language of expected number is something very much with discrete random variables. Like when I see the words expected number, I do think mean, but a lot of times it's a discrete random variable, and I can treat these as probabilities. And now knowing that, and so what did it come out to be for the E? Or what is the expected value there?
15.62.
So 15.62. Right? Don't ever round your expected values because it is an average, right?
4.5.
I mean, that's enough.
Okay.
Yeah, I'm just saying don't round it to 16 or something like that.
Okay.
But what do we still need?
Standard deviation.
And so this is why you want to identify what type of concept are we dealing with. Once we recognize, hey, it's binomial, there's literally a formula for mean on binomial, right? What does it give us for standard deviation?
It's the square root of the mean times the complement probability.
You look at that formula sheet, right? And that's what Ashton keeps referring to, is that mean is right here, times the probability of failure, or it's just 2,000 times, what was this decimal, 0.077?
0.78.
Okay,
Like, no, it's like 2 zeros.
2 zeros, got it. 0.078. And so I would use the calculator, and then I would just get 0.9922.
Yeah.
There's my standard deviation, once I plug that in. So if you identify what type of variable or probability you're dealing with, then that makes it super easy, just use a formula sheet. And again, I don't remember who said it, but the recognition that it's either model E or it's not model E, that's binary, and that makes me think about that binomial right away.
Is that a 1?
1 minus P?
Okay.
Yeah.
I'm getting it for my.
Because remember, P is your probability of success, so 1 minus P is the probability of failure. Alright, how are we feeling about that? Yes, ma'am?
Where did the 0.0078?
That's the 2,323 divided by the 297,000.
And what about the 0.992?
So remember, that's 1 minus P. So remember, P is my probability of success, so that's how many owners there were of car E out of all of these owners,
So it's 1 minus that number?
is what gives me this. And you can just put that in the calculator, you don't have to know that off the top of your head. But another way, remember to think about it is probability of success, probability of failure. Okay? Alright, whatever that is. Part B, when selecting a simple random sample of 2,000 new car owners, how likely is it that fewer than 12 owners of Model E would be included in the sample? If we did our job in A, this actually becomes pretty easy. What is B? How are we going to tackle it?
Use Z-score.
You could, but there's an easier way. Huh?
I probably got a Z-score.
But what type of distribution do we identify in A?
Binomial.
We identify this one as binomial, right? Remember, it's not the first success, it's fewer than,
Oh,
and this one is fewer than
12.
12, right? So we would want to notice binomial. Could we convert it to a z-score? 100%.
Oh, can you use binomial CDF?
You can do binomial CDF in this case. And so I will say this is more binomial, but I think I even showed y'all an example, and it's going to come back up within the next unit. I showed y'all that on the calculator when, I think it was if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, wasn't the binomial approximately normal?
Yeah.
And so you can do either direction on that, right? So we identified a mean here, we identified a standard deviation here, we can convert it to a z-score, but personally I'm going, hey, it's a binomial CDF with a lower bound of 0, upper bound of 11, and then you would just use this as your probability of success. What would be your number of trials?
2,000.
2,000, right? So that's all I would personally do here. So I would say binomial, I would say lower bound of 0, upper bound of 11. That probability of success is 0.0078. And then the number of trials is 2,000. You identify something like that, you put it into the calculator, you'll get the correct answer. But again, you can do a normal CPF if you want. But if you do a normal distribution in z-score, you need to draw that normal curve out. Okay? C. This is actually more of a review, but this is important to always consider what we've learned in the past. The company is concerned that a simple random sample of 2,000 owners would include fewer than 12 owners of Model D or fewer than 12 owners of Model E. Briefly describe a sampling method for randomly selecting 2,000 owners that would ensure at least 12 owners will be selected for each of the 5 car models. Stratification, right? Notice, because we have such a huge percentage right here, we're more likely, if it's a simple random sample, to get most, if not all, from here. But what is it when you have homogeneous groups that are distinctly different from each other? A stratification is a great process. And the stratification process that you would want to use, now we'll point this out, would you want the same number from each of these sections?
No.
No. I would do 112,338 out of 297,354 and multiply that by 2,000, right? That's how many I would select out of Model A, right? So the percentage that have Model A, that's the percent that I would want from Model A. The percent from Model B, that's the percent I want from the sample. And so that's what I would do. I would not do the same amount for each. Does that make sense?
No, I'm dying.
Stratified random sampling would be a great option there. Don't forget though, when you talk about that stratified random sampling, what do you have to always talk about when you explain the random sampling process?
Random number generalization.
Something before randomization.
Oh.
Assignment.
You need to assign every individual a number. Then you can't just say randomize, you have to use a random number generator to select, to generate X number of numbers, and then you select those individuals. Okay? So assign, generate, select.
SAG.
Assign, generate, select. AGS, I guess. I don't know. Alright. Think Texas A&M the Aggies, I guess. I don't know, but I hate Texas A&M, so don't think like that. I don't know. Anyway, so do as much as you can. Come in with those questions tomorrow to start the day.
Are we done?
We're not done. We gotta start the next unit. Yeah, we are doing that as well.
I haven't got that video, so.
Alright. So, the notes that I gave y'all yesterday. Yep, gave you notes yesterday.
There's a no
It
left.
says chapter 7 at the top.
And
Pretty sure I gave them to you.
yeah.
That's it.
I'm actually and the
Yeah.
fair model.
So, I gave y'all the Frere model today. Gave you the notes yesterday, sampling distributions.
Fair model.
Oh, yes.
Literally, look.
The one right here.
I can't
Right
do this
here?
anymore.
I don't have paper to do that one.
Oh, yeah, it is that one. Okay. I seen a whole bunch of it.
I promise you I'm taking notes.
I see that. You're awake today. I'm proud of you. All right. Hey, guys, we've talked about these things before. Notice what page can you read more about this? 441 to 443, okay? I've gone through the notes, made sure all the pages are correct. But what do we remember? What is a parameter? That's a population. So yeah, statistic is just for a sample. So it's a population value
Okay.
for some characteristic. Okay? So a parameter is that population value for some characteristic. characteristic. What is a statistic then?
Sample value versus whatever.
Okay, so it is a sample value, which there's probably a slightly better wording for this in the book, but these are the ideas. Make sure you read the book for some characteristic. So how are they related?
As
You can use the statistics and for
the
the
sample size approaches infinity, it approaches the.
Be careful in that like sample size approaching infinity, because I can't do that. But as sample size gets larger, there may be something there. But let's listen to what Joseph said. What'd you say, Joseph? What's the whole point of a
You
statistic?
can use the statistic to infer the parameter,
Because what is that statistic doing? It is,
representing the population.
yeah, so be careful. The sample, if we did good sampling, the sample represents the population, right? But what does that statistic do? The statistic,
Inference value.
it allows you to make an inference because it is, it's an estimating. Statistics estimate parameters. That's it, right? Like that's what a statistic does. A statistic estimates the parameter. That's why we need our samples need to be what of the population? Representative of the population. So we can make what? Oh, I love that word. Say that word again. Accurate what? Inferences. Be representative of the population. So researchers can make accurate inferences. That is the whole goal of statistics, guys. We want to collect data from a sample and we want to use that sample to make some inference about that population.
5 minutes in, we finally found the purpose of
What'd you say?
5 minutes in, we finally found the purpose of statistics.
I mean, to be fair, I told you all this at the beginning, but we've really started to actually like get into it, and it's come up over and over and over again, right? We have been doing this the whole time, but that's why we're doing all this. I just always want that reminder there. That's the whole point of statistics. Okay. All right. I want you just quickly, let's say 4 minutes, get as much of A and B done here while I set up a couple of things. Mr. Ellis, can I get you to help me grab these distributions?
I can't hear myself think when you over there.
LMAO, you have to write. I was thinking this whole lesson, I didn't write it.
Yeah.
I don't think, my brain just goes radio silence.
Right now, I'm silent. So.
Make those as far right as possible.
I don't do that.
When I go home, maybe past
Hey,
7,
have you finished doing A and B?
with excellent representation.
Huh?
I'm lying.
I'm aware. That's why I felt the need to call you out.
Thank you so much.
Thank you for getting back on task. Do this for me. Put right there.
Why are you having stuff like this? Not even asking questions. statistic would be if they had a cell phone, correct?
In the
What?
distribution of
Statistic would be, yes, or no, so.
10-year-old boys are like the population, right? So the 75th percentile in that distribution
What's the statistic?
parameter.
But it's of the sample though.
But you,
No.
you don't have to say.
Where's she, how's she calculate the
Specifically the question or the answer to the
That's
question?
statistic.
How do we define a statistic? It is a value, right?
So it'd be 71%.
Yeah, that's the sample. So when
Haley,
she,
you're right with
that's
that.
a statistic. Like sample.
Oh, I'm getting parameters mixed up, I'm sorry.
Well, it says identify all.
Thank you for your patience.
Identify all.
Okay, so the statistic, whatever, is 70% saying yes, because the statistic is a value. It says okay, so Haley, you're right as always.
Well, well.
In most
I might be
institutions.
right on that one part, common sense wise. I did write that down. I did.
Yeah, population would be
See, that's where I got.
12 to 17-year-olds in the United States, right?
There's like Vaseline or something
Yeah.
on the table.
Your population
You're
is,
talking about like that weird like black stuff.
You didn't even write down sample.
your
Sure,
population,
I'm about to do it.
And I was on my
population-
pencil. I put my pencil down.
I'm about to do it.
My hands.
Okay, first of all,
That's
period.
my pencil.
okay, so basically your population is basically, it's the thing past the number. If it's like 1102 yada yada, usually your population would be yada yada.
I was like, what is that?
Unless it's like a special case.
I give that thing a 70%.
Alright. So, we got 5 minutes. Eisenhower's up here. Population, all 12 to 17-year-olds in the U.S. The sample then is the 1,102 that were randomly selected, right? The sample is who we get our data from. The parameter, I need you to pay attention to this language. Do we have the parameter here? No, the language I used was the,
Probability.
look right, well, look what I wrote. Not just proportion, the what? True proportion. We don't know what the true proportion is, do we?
No.
No, but that's the goal, is the true or population proportion. On the AP exam, and when you hear statistics a lot of times, when we talk about the population value, we say the true proportion, the true mean. We don't know it yet. We're going to be estimating those things. But the parameter here is an unknown, but it's the true proportion of 12 to 17-year-olds who have cell phones. And so what is the statistic?
The value.
The value of 0.71. Notice how I use p hat here. Statistic is p hat. The parameter is just p. You see how it looks like a little hat on top?
Is that the actual name for it?
Yeah, that's literally the name for it. That's not me making that one up. It's called p hat. We will study linear regressions later, and it's y hat.
So p hat is the statistic.
Yes. I will say this. That hat literally just means predicted. Like the predicted y value, the predicted sample proportion. All right. We didn't do B yet. I do want you to think about that, but I want y'all to see something right here, which I feel like something went off because I don't know how these got up there accidentally. But I want us to notice something. This is what we've been building. And when Michael Wynn was complaining, if you heard him complaining about doing all those dots, does anyone know what this is right here?
Dot.
What is the dot plot of though?
Of the
Year in which the pennies were made.
of a sample?
Is it of the sample?
Oh, it's a sample district. Wait,
You
why
should
should
make Michael do that.
Because he's my TA. And
That's so informal.
Poor Mike.
oh no, I asked him to do one thing all semester. No, this is actually every single penny that's in that box.
It's a junior one.
Oh.
Well, it's not every single.
This one right here.
Is that legal?
Oh.
That?
Yeah.
You don't have time.
Poor Michael.
Okay.
You gotta start paying him, Mr. Kenny. I would cry.
What are you?
I just like.
He's a TA. I asked him to do nothing else. All right, guys, shh, listen, okay? This though is the population distribution. That's what this is. The population distribution of the year those pennies were made. I need to write that down here later. So right here, what did we have? Just the year of the penny, right? But how many did we collect here? Does anyone remember? But each dot only represented one penny. Okay? Now then we started doing sample sizes of 5 and sample sizes of 5. And then we started doing sample sizes of 20 and sample sizes of 20, which is supposed to be Oh, I guess someone just put it there. That's that far. Okay, so this has a parameter, doesn't it?
Yes.
Do we know what the average year the penny was made is?
You can find it.
You can find it, but do we know it right now?
I don't know.
No. But what did we do? We collected
Data.
but what are we going to call these dots down here? These are what?
Statistics.
These are, well, we collected samples and we got statistics out of those samples, right? Any guesses what the average of these statistics and the average of this population might have in common just looking at it? When I'm looking at it, I'm seeing like my average might be somewhere around here, right around the year 2000. What does it look like my average is right here? Oh, crap. Wait, so you're telling me the average of the population distribution and the average of this is called a sampling distribution because it's a distribution of what? Samples, right? So the averages are the same? What do you think the average of this distribution might be?
They're not exactly.
Maybe a little bit less, so maybe we're a little off. Maybe somewhere around 1997? Because you mentioned earlier when we increase our sample size, it's going to make our samples more what? Accurate, right? But also I want you to notice this has less spread, right? So we're going to talk about this more heavily tomorrow, but please notice when we do those sampling distributions, the mean stays the same, but the spread, as we increase that sample size, what happens to our spread? It decreases. Like notice how spread out this is versus how spread out this is. A whole lot less spread when we increase that sample size. Yes, 100%. You can take those. Yeah, if you can come back later to grab them. Actually, Mr. Arliss, we don't use the calculators in Algebra 2. Yeah, guys, we're not using calculators in Algebra 2, but if you borrow one, make sure you bring it back before school tomorrow so that my students can use it.